Hi there, my name is Brandon and welcome to the next video in my series on basic statistics. If you are new to the channel, welcome and it's great to have you. If you're a returning viewer, it is great to have you back. If you liked the video, please give it a thumbs up, share it with classmates, colleagues, or friends, or anyone else you think might benefit from watching. So now that we are introduced, let's go ahead and get started. So a quick review from the previous video. Here is our data. We have 12 salary observations. Now, we're going to hypothesize that the median of this data is $60,200, which is there between the third and fourth observation. Now remember, when we're talking about the median, we are proposing that the proportion of observations is actually half. So by definition, the median is where half of the observations are below the median and half of the observations are above the median. Now, what we do in the sign test is we put plus signs next to each observation that is below our hypothesized median. And then we put negative signs on every observation that is above our hypothesized median. So it looks like this. Now, we have 3 out of 12 observations that have plus signs. So that is 0.25 or 1/4 of our data set. So that's our proportion. Now, the hypothesis for the median is that it's 0.5 or half. So here in the middle, we have an arrow that is our actual median. And then over here on the left, we have a darker arrow that is our hypothesized median. So do you think those two things are equal? Let's find out. Here's another situation where we actually have the arrow on the median. So our hypothesis for the median is actually the median. So we have half below and half above. So in this case, we know we would not reject our null hypothesis because it is by definition half of our observations. So we put plus signs for the first 6, negative signs for the second half. That's 6 out of 12 or 0.5. So our proportion is 0.5, which by definition is the median. So what about a median of $97,600? That is between the 10th and 11th observation. So we put plus signs on every observation below and minus signs on everything above. So now we have 10 out of 12, which is 0.833, and our hypothesized median is 0.50. So is 0.833 similar to 0.50? It doesn't really look like it, but we'll go ahead and do the test and find out. So here's everything on one slide. In the first case, we have a median that we propose is between the third and fourth observation. Now notice here that I changed the median to 3.5. It's not 60,000 or whatever it was. In non-parametric statistics, it's very important to note that oftentimes, if not in most cases, the actual values of our data don't actually matter. What actually matters is the location of our observations relative to each other. The most common way we relate our observations is by sorting them, like we did in this example. So our first hypothesis says that the median is halfway between 3 and 4 approximately. Now our second hypothesis states that the median is right down the middle, so between the 6th and 7th observation. And then finally, our third hypothesized median is between the 10th and 11th observation. So there's everything on one slide. Now, of these 3 options, which one do you think is most likely the actual median? Well, obviously, it's the one that goes right down the middle. But we do need to look at the other 2, and I'll tell you about why that is here in a second. So we have location 3.5 and location 10.5. So the way we're going to test this is by using the binomial distribution. So if we were to get 10,000 people in an arena or something similar, and they each had a coin, and we wanted to have those 10,000 people take the coin out of their pocket and flip it 12 times. This matches our 12 observations we have in the salary data. So 10,000 people in the arena all flip a coin in their pocket 12 times, and then they record the number of heads they get out of those 12 coin flips. Then what we have them do is we take out their smartphone and we have them just enter into a poll or some other online recording system the number of heads they got. And then we take all 10,000 of those observations or experiments, and then we put the results up on the board, like up on the big TV, or what we call a jumbotron here in the US. This is what it would look like. So the most likely outcome in all those experiments is getting 6 heads out of the 12 flips. And then, of course, on either side of that, the next common would be 5 and 7 heads. So while you could have 0 heads, it's very unlikely. And that's what we're doing here in the sign test. When we're proposing or hypothesizing about where the median of a data set is, what we're doing is testing whether or not it falls here in the middle, where the most likely outcome is. So you can think of the sign test in a very similar way. What is most likely if we have, 16 observations? If the median is what we say it is, we would expect to have 8 plus signs below the median and 8 minus signs or negative signs above the hypothesized median. That's where we'd expect it to be. So first, let's look at the 3 plus signs example. I'm going to walk through this step by step, so don't worry. So here is a table that I copied over from Excel. But I want to explain what each column is telling us. So in the first column, which is column A, actually, we have the number of plus signs that are possible. So in the first case, we could have 0 plus signs. So we have negative signs all the way across, and that is technically a possibility. Now think about that. If we don't have any plus signs in our sign test, is it likely that that value is our median? Well, no, of course not. But what about the other extreme? What if we have all 12 are plus signs? In that case, our median would be way off to the right. Is that likely the median of our data? Well, no, it's not. Where is the most likely location? Well, it's right in the middle. So if we look at the probability column, we're using the binomial distribution, we can see that the highest probability is 0.226 at the location of 6 plus signs, which, of course, out of our 12 observations, is right down the middle. So finally, let's discuss the third column. Here, these are just the formulas we used to get the value in the second column under probability. We're using Excel's binom.dist function, and it takes a few parameters that we have already here with us. So the A2 in that formula represents the value over there in column A, which in this case is 0, 1, 2, 3, and so on. 12 is the number of observations or trials we have. 0.5 is the probability of either outcome. So in this case, it's plus or minus. And then false is just something we put into that formula to get the exact probability we have here in the second column. If you have any more questions about the binomial.dist formula, or this formula here, the function in Excel, just do a search for it and you'll see kind of how it works. But in this case, we're just saying, hey, what's the probability of getting 0 plus signs or 0 like heads in the coin flip example? If we have 12 observations, the probability of each outcome is 0.5, and then false, so we get that exact probability. This is all this is. So what we're saying is the median, or hypothesizing at least, the median is $60,200. So here is our null hypothesis and our alternative hypothesis. So the probability of 3 or fewer plus signs is just the sum of 0 through 3 over here on the left. So we take the first 4 probabilities for 0, 1, 2, and 3, add those up, and we get 0.073. Now, our test is two-tailed because we did not specify otherwise. So it's a two-tailed test. So what we have to do, all we have to do, is take that probability, the sum of 0, 1, 2, and 3, and multiply it by 2 because of the two-tailed nature of our test. When we do that, we get a probability of 0.146. We set an alpha level of 0.10 for this test. Now, because our p-value is greater than alpha, we cannot reject the null hypothesis. So think about this. We are hypothesizing that the median of this data set is $60,200, which is between the third and fourth observations here. Now, we would think that's kind of crazy, right? We have this hypothesis and we're only going up between the third and fourth value out of 12. And because of the probability, we cannot reject the null hypothesis of $60,200. Well, there's a reason for that. And that's because of the small sample size we have here. So when we only have 12 observations, it doesn't take much to tip our probability over our chosen significance level, or our alpha. So the reason that we cannot reject the null hypothesis here is mainly due to sample size. So for the 6 plus signs, this is actually self-explanatory. This slide is in some ways nonsense because, of course, out of 12 observations, 6 is kind of what we would expect the median to be. So median of 76,200, there are a null and alternative hypothesis. Of course, we cannot reject the null hypothesis because it is literally equal to the median we proposed. So what about the 10 plus signs example? So here we have a median of $97,600. Here are null and alternative hypotheses. So the probability of 10 or more plus signs, we could do one of two things. We could just add up the 0.16, 0.003, and so on. Or we could take 1, which is the added probability, the sum of the probabilities here in this column, and then subtract the probabilities that go from 0 through 9. It doesn't matter. We could add up the 3 probabilities here at the bottom, or we could take 1 minus the first 9 plus signs there on the left-hand column. Same result. Now this test is two-tailed, so take a probability of 0.019, multiply that by 2 because of the two-tailed nature. We end up with a p-value of 0.036. Remember, our alpha was 0.10, and therefore we would reject our null hypothesis and conclude that the median of our data is not $97,600. You kind of see how this works. You have to take what you know about the binomial distribution, which you probably learned back in finite mathematics or in earlier chapters in statistics, and just use that to figure out this scenario where you have plus signs and minus signs. And all you're doing is counting up the plus signs and seeing what is the probability of getting that number of plus signs in your data based off the binomial distribution. Now, if our sample size is a little bit larger, say around 20 or so, what we can do is actually use the normal approximation of the binomial distribution. So around a sample size of 20 or 30, some textbooks will differ on this, but we'll say around 20, the binomial distribution, which remember is a discrete distribution. So remember in the plus signs example or the coin flip, you either have 0, 1, 2, 3, 4, 5, 6, whatever it is, number of plus signs or number of heads. There is no like 7.3 plus signs or 9.7 heads. That's what we mean by a discrete distribution. It's a whole number of plus signs, or in the case of the coin flip, the number of heads you got. But when we're approximating the binomial distribution using the normal distribution is a continuous distribution. So that's what we call it, an approximation. Now, as your sample size gets higher and higher and higher, those two distributions, they converge, and the shapes are essentially the same. Now, when we are using the normal distribution as an approximation, because our sample size is large enough, our mean is defined as 0.5 times our sample size. Well, that should make sense. That is half of our sample size, which would be the middle of our data once we line them up in order. The standard deviation is the square root of 0.25 times our sample size. So again, if we're using the sign test and our sample size is large enough, we can use this normal approximation to the binomial distribution to keep us from having to add up a crazy number of probabilities. As you remember the previous slide, we have 0 through 12 probabilities. We would have to add up certain parts of those. This makes this a whole lot easier. So here is another problem using a larger sample. So HR says the median salary for your company is at least $75,000. This is part of their marketing or recruitment efforts. However, a sample of 86 salaries found that 34 of those salaries were greater than $75,000. Now, one salary in our data was exactly 75,000. So remember, for the sign test, we discard that salary because we can't put a plus or minus because it's not above or below our hypothesized median. It's actually on the median. Therefore, we throw it out and use one less. So our sample size after throwing that salary out is 85 salaries. And consequently, 51 salaries were less than $75,000. That's our 85 total minus the 34 that were greater than 75,000. So 51 salaries were less than 75,000. Now in this problem, we will conduct a one-tailed test because remember, HR said the median salary is at least $75,000. So when you see at least instead of equal to, you're talking about a one-tailed test. And again, because our sample size is high enough, we'll use the normal approximation to the binomial distribution. So our null hypothesis is that the median salary is greater than or equal to $75,000. And therefore, our alternative hypothesis, were we to reject the null, is that the median salary is actually less than $75,000. So graphically, it looks like this. So we put all of our salaries in order, and we have 51 that are below 75,000, and we have 34 that are above 75,000. So HR is proposing that the median is located right there where you see the color change in the bar and where the $75,000 label is located. Now, think about this. The actual median of the data is where this thinner line is. So HR says the median is over here where 75,000 is. Your data says the median is here where the thin line is. Now the question is that difference there enough to fail to reject the null hypothesis and therefore HR is correct? Or is it enough to reject the null hypothesis and therefore HR was incorrect? And that's what we're going to do in this problem. So again, we will use the normal approximation. So here are our null and alternative hypotheses. So the mean, remember, is 0.50 times n, our sample size. Standard deviation is the square root of 0.25 times n, which is our sample size. So we go ahead and do those. So we have 0.5 times 85, because our sample size is 85 observations. So our mean is 42.5. The standard deviation is the square root of 0.25 times our sample size, and that comes out to 4.61. Now, because we're using a normal approximation, we can use the normal distribution like we did very early in statistics. So our p-value we're trying to find, what we're saying is, what is the probability that the number of salaries that are greater than $75,000 is 34 or less? So I'm going to say that again. What is the probability that the number of salaries that are greater than $75,000 is less than or equal to 34? Remember our graphic. Now we have to do what's called a continuity correction factor. Because we are approximating a discrete distribution, the binomial, using the normal distribution, which is continuous, we do what's called a continuity correction factor. And that is actually determined by the symbol in the probability statement above it. So here it's less than or equal to, and then when it's that, we add 0.5. So here our p-value is the probability of the number of salaries that are less than or equal to 34.5. So now we can just use a z-score or a z-value that we learned earlier in stats. So we have 34.5, which is the number of salaries that we're looking at, minus the mean salaries we would expect if the middle is where we think it is, divided by the standard deviation. So again, this is just a z-score. So we go ahead and do that math out, and we end up with a z-score of negative 1.735. And now we will use that z-score to go into the back of our book or use an online tool, whatever else it might be, to find the actual probability in that part of the normal distribution. Let's do that next. Okay, so what will we expect under a couple different situations? So here is the ideal situation. In this case, we have half of our observations below our mean our median and half of our observations above our mean or median. And I'm using those interchangeably because remember, we're using the normal distribution as an approximation of the binomial distribution. So you can see here that I set the mean to 42.5. That's what we got from our formulas before in the normal approximation. And the standard deviation to 4.61, again, which comes from our formulas from the normal approximation. But we're not asking about this. This is the ideal situation. What we're asking is, what is the probability of 34 or fewer? This says plus signs, but I actually meant observations because the 34 are actually in the upper tail. So what is the probability of 34 or fewer observations in the upper part of that distribution? So what is the probability of 34 or fewer salaries that are greater than or equal to $75,000? Remember, that's the area to the right of our median where HR says the actual median is located. Now, when we do that, this is what we get. So instead of half and half, what we have here with a mean of 42.5 and a standard deviation of 4.61, again, using the normal approximation, is that the probability of having approximately 34 observations in that part of the distribution or less is 0.0413. So we get that from down here on the right of our distribution, and that is the area below. Remember, our z-score or z-value was negative 1.735. So you look there on the distribution, you can see that the shaded area begins right at, if you just kind of eyeball it, it's 1 standard deviation, and then you go about 3/4 of standard deviation, and that's where the shaded area begins, and then everything below that. So what we were saying is that the probability of having 34 or fewer observations in the right of our diagram, where HR says the median is actually only 0.0413. So here's our hypothesis test. We have a p-value of 0.0413. If we set an alpha of 0.05, what we'd have to do is reject the null hypothesis. So our null hypothesis said the median salary in our data is greater than or equal to $75,000. Well, our test said, it's very unlikely, in this case, below our alpha value, unlikely, that if the median salary is greater than or equal to $75,000, that there would be 34 or less values above the hypothesized median. So therefore, we reject the null hypothesis and conclude that the median salary is actually less than $75,000 as it was claimed to be. Now, always use common sense to go back and check the conclusion. In this case, 51 of the 85 salaries we're working with were less than $75,000. So the rejection of our null hypothesis makes sense. If HR says the median salary is greater than or equal to $75,000, but 51 of the 85 salaries are actually less than that, we should be skeptical. Now, visually, it looks like this. So here are our salaries. We had 51 that were below this threshold of $75,000. We have 34 that were above that hypothesized value of $75,000. The actual median is there where the thin line is. Now, this should make sense. Remember, what we were testing is this part of the bar over here on the right where the 34 is the actual median there? Is it at $75,000 or is it even higher? Now remember, if the hypothesized value of the value is even higher, the number of salaries in this right part are going to go less and less and less below 34. That's why when we did our normal distribution approximation, we were finding the probability that this part of our visual here was 34 or less. And you can see as this 34 would go down to 33, 32, 31, this part of the bar would get smaller and smaller and smaller, and that hypothesized median would get further away from the actual median, which is here where the thin line is. Quick review. So the sign test is a non-parametric method for testing a hypothesis about the median of a data set. We We convert each value into a plus or minus sign, depending on if it falls below or above the hypothesized median, respectively. Then we count the plus signs and implement the binomial distribution. So if an observation is the same as the hypothesized value, those observations are removed and the test continues with a smaller sample size. Now, if the sample size is larger than 20, we can use the normal approximation to the binomial distribution instead of adding up, countless probabilities like we had in that table before. And I will add here, try to keep in mind what you're asking yourself. Draw visuals out if you need to. Because remember, because of the combination of the one-tailed test we were doing and where those values fell in that visual, we were actually trying to find out the probability of having 34 or fewer observations that were above that hypothesized value for the median. So we had to think about the problem a little bit differently to make sure that we were getting exactly what we were looking for logically. Okay, so that wraps up this video on one of the first methods you will learn in non-parametric methods, non-parametric statistics, and that is the sign test. It's just as simple as putting all your observations in order, putting plus signs on one side of the hypothesized median, minus signs on the other side of the hypothesized median, and of course, if you have something that's exactly what you hypothesize, you toss it out. And then you use the idea of the binomial distribution to figure out whether or not where your hypothesized median falls, does that meet the criteria of either rejecting your null hypothesis or failing to reject your null hypothesis. Now remember, when you're doing a test like this, it's very rare, if ever, that the value you hypothesize to be the median is going to fall right in the middle of a data set. Now, just because it doesn't fall exactly in the middle of the data set does not mean that your hypothesis will be rejected. There is an area near the middle where the hypothesized median can be, and because of the nature of probability and statistics, you would still fail to reject that null hypothesis. There's sort of a window or an area in there. So now you know how to do that if you have data where you cannot make any assumptions about the underlying distribution. So this is salary data, but of course it can be used in other situations and other types of tests where the numbers may not quite make as much sense. So thank you very much for watching. I appreciate your time. I wish you the best of luck in your studies, and I look forward to seeing you again in the next video. Bye-bye.